stands for Retrieval-Augmented Generation. This is one of the most widely used AI patterns in production today. By the end of this video, you will have a working system that answers questions from your own documents using a language model running locally on your machine. Let's see. What is it? Here is the core problem. AI models like Claude and GPT-4 are trained on enormous amounts of internet data. They know a great deal about the world in general, but they know absolutely nothing about your specific company, your internal policies, your product details, your support documentation, anything that was not in their training data. RAG solves this by giving the AI access to your documents at the moment it answers a question. RAG stands for Retrieval-Augmented Generation. Let us break each word down. Retrieval means finding something, in this case, finding the most relevant pieces of your documents. Augmented means enhanced or supplemented. The AI's prompt is enhanced with the retrieved content. Generation means the AI writes the final answer based on everything it has been given. So the full meaning is, find the relevant pieces of your documents, add them to the AI's prompt, and then generate an answer using that information. Think of it like a new employee asked a tricky policy question on their first day. They do not know the answer off the top of their head. So they search the company handbook, find the 3 most relevant pages, read them quickly, and then answer the customer using what they just found. RAG does exactly this, automatically, for every single query. Let's see the workflow. RAG has 2 separate pipelines, and understanding which is important. The first pipeline is the indexing pipeline. It runs once when you add documents. It loads your documents, splits them into chunks, converts each chunk to a vector, and stores everything in a vector database. You already built this in video 3. RAG builds directly on top of it. The second pipeline is the retrieval pipeline. It runs every time a user asks a question. Step 1. The user submits a natural language question. Step 2. The system converts that question into a vector using the same embedding model used during indexing. Step 3. It searches the vector database for the chunks whose vectors are most similar to the question vector. This is called similarity search. Step 4. The top results, typically the 4 most relevant chunks, are added to a prompt template alongside the original question. Step 5. The language model reads the prompt with the context and generates an answer based only on what it finds there. The vector database sits in the middle. Indexing writes into it, retrieval reads from it. It is the bridge between the 2 pipelines. Look at the tip at the bottom of this slide. Always add this sentence to your prompt. If the answer is not in the context, say "I don't know." Without this instruction, the AI will sometimes answer from its general training data when the provided context does not contain the answer. This produces a confident-sounding but potentially wrong response, which is called a hallucination. This one sentence prevents it. Next, key concepts. 3 things to understand deeply. First, the indexing pipeline. This is the setup phase. You load documents, split them into chunks, convert each chunk into a vector using an embedding model, and store those vectors in a database. A vector, as we covered in video 3, is a list of numbers representing the meaning of a piece of text. The indexing pipeline creates the searchable knowledge base that the retrieval pipeline reads from. Second, the retrieval pipeline. This is the query phase. When a user asks a question, you convert that question into a vector using the exact same embedding model. You then search the vector database for the stored chunk vectors that are numerically closest to the question vector. Closest in mathematical terms means most similar in meaning. You retrieve the top 4. The K parameter controls this, where K stands for the number of results. Those 4 chunks are inserted into a prompt template as context, and the language model generates the answer. Third, the hallucination guard. Hallucination is the term for when an AI model generates a confident but factually incorrect response. It happens because the model is trained to always produce a response, even when it does not have the relevant information. The guard is a specific instruction in your prompt. If the answer is not in the context, say "I don't know." This forces the model to stay within the boundaries of what the retrieved chunks actually say, rather than filling in gaps from its general training. Next, let's see project setup. Install all the required packages. LangChain is the core framework. LangChain Community contains the Chroma integration. LangChain Ollama is a separate package for the Ollama integration. It is easy to forget and causes a common error if missing. ChromaDB is the vector database library. Sentence Transformers provides free local embeddings. PyPDF is for reading PDF files. You will have two Python files. The ingest.py file is from video 3. You run it once to index your documents. The rag.py file is new this video. It reads from that index to answer questions. The most important prerequisite is on the right side of this slide. You must run ingest.py at least once before rag.py will work. The chroma_db folder must exist. If it does not, rag.py will fail immediately because there is nothing to search. Let's create how to create rag.py file with Ollama. This is the completely free version. No API keys, no cost, runs entirely on your machine. The code has 4 parts. First, you load the vector store using the same Hugging Face embedding model that was used in ingest.py. You point chroma at the chroma_db directory where the vectors are stored. Second, you define a prompt template. A prompt template is a reusable text structure with placeholder variables. The 2 variables here are context, which will be filled with the retrieved chunks, and question, which will be filled with the user's query. The hallucination guard instruction is included in this template. Third, you create the Ollama LLM object. This connects to your locally running Ollama instance and uses the Llama 3.2 model. Fourth, you build the Retrieval-QA chain. Retrieval-QA is a pre-built LangChain component that connects the retriever, the prompt template, and the language model into a single callable chain. The search quargs parameter with k equals 4 tells the retriever how many chunks to return. The return source documents flag makes the chain also return which document chunks were used, so you can show users where the answer came from. Let's create how to create rag.py file OpenAI. The OpenAI version is nearly identical to the Ollama version. The differences are in 3 lines. First, you import chat OpenAI and OpenAI embeddings instead of the Ollama equivalents. Second, the embeddings line uses OpenAI embeddings, but only if you also used OpenAI embeddings in ingest.py. If you used Hugging Face embeddings in ingest.py, keep Hugging Face here too. Mismatching them is the most common mistake in RAG. Third, the LLM line becomes chat OpenAI with GPT-4o mini and temperature equals 0. Temperature is a parameter that controls how creative or random the model's responses are. A temperature of 0 means the model always picks the most statistically likely next word, making it deterministic, meaning it gives the same answer every time for the same input. For factual question answering, this is what you want. Everything else, the prompt template, the Retrieval-QA chain, the k parameter, stays exactly the same. Let's create how to create rag.py file with Anthropic. The Anthropic version demonstrates a very practical cost-saving combination. You use Hugging Face embeddings, which are completely free, for the vector search step, and you only use the paid Claude API for the final answer generation step. This makes sense because embedding calls happen silently in the background. If you have a high query volume application, using free local embeddings for search, while only paying for the language model's generation step, significantly reduces your costs. The only line that changes from the Ollama version is the LLM line. Instead of Ollama LLM, you use chat Anthropic, with the model name and temperature equals 0. Everything else is identical. Same prompt template, same chain, same retriever configuration. This highlights an important design principle in LangChain. The chain does not care which provider you use for the LLM. You swap one object and the entire pipeline works the same way. Next, Fast API endpoint. This shows how to expose your RAG system as a web API that any front-end or mobile app can call. The most important detail here is where the setup code is placed. The embeddings, vector store, language model, and chain are all created once at the module level, meaning they run once when the server starts. They are not created inside the route handler. This matters because creating the embeddings model and loading the vector store takes a few seconds. If you did this inside the route handler, every single request would wait that long before getting an answer. By creating them once at startup, all subsequent requests are fast because they reuse the already loaded objects. The route handler is small and clean. It takes a question object with a query field, passes it to the chain, and returns both the answer text and the source document metadata. The source metadata tells the caller which files and pages were used to generate the answer. Let's compare. 3 options, each with a clear use case. Option A with Ollama is completely free and works offline. It is the best choice for learning and development. The only limitation is that older or lower-powered machines may find the local models slow. Option B with OpenAI gives you GPT-4o Mini, which is fast, accurate, and the cheapest OpenAI option. Use this when you are ready to deploy to real users and want a reliable hosted model. Option C with Anthropic gives you Claude, which has particularly strong reasoning and reading comprehension. This is well suited for complex documents where nuanced understanding matters. Look at the recommendation bar at the bottom. The best cost combination is Hugging Face embeddings, which are free, plus Claude or GPT for generation only. You pay only for the language model's answer generation, not for the embedding searches. Let's see the common errors. If you see a file not found error for chroma_db, you have not run ingest.py yet. Run it first. If similarity search returns irrelevant results, you have a mismatched embedding model between ingest and RAG. They must use the exact same model. If the AI gives confident answers about things not in your documents, the hallucination guard is missing from your prompt. If you get a module not found error for langchain_Ollama, install it separately with pip install langchain Ollama. If you get a connection error for Ollama, check that it is running by opening a browser at http localhost 11434. If you get a context length exceeded error, reduce k from 4 to 2, or reduce the chunk size in ingest.py. Context length refers to the maximum amount of text the model can process in one request. Too many large chunks can exceed this limit. If the model says "I don't know" for every single question, your ingestion did not work correctly. Go back to query.py from video 3 and verify that relevant chunks exist in the database. So here are the takeaways. RAG means search your documents first, then let the AI answer using only what it finds. The AI never guesses when the context is present. There are two pipelines. Indexing runs once to build the knowledge base. Retrieval runs per query to search and answer. The vector database connects them. The hallucination guard is non-negotiable. Add it to every RAG prompt. A confident wrong answer is worse than an honest admission of uncertainty. The embedding model must be identical in both ingest.py and rag.py. This is the single most common source of broken results. The best cost combination is free Hugging Face embeddings for the search step, plus a paid model like Claude or GPT only for the final answer generation step. Next up is video about caching, where you learn how to return stored answers instantly with zero API cost for questions that have already been answered before.